Hi, in this video I'm going to talk about linear differential equations. Don't forget to subscribe my channel and like the video. Linear differential equations are really important in physics, actually in dynamics and oscillations. And oscillation is everywhere in nature, actually. Everything is oscillating around us. So we should know linear differential equations as a mathematical tool to describe the oscillatory motion. And this is a really important topic in physics, in classical physics, and in quantum mechanics. And the reference that I'm using for this video is David Morin's Introduction to Classical Mechanics. This is a really fantastic book and is recommended for you to go and solve some of its oscillation chapter problems after this video. First, I start with the definition. And this definition is the definition of x of t. X as a function of t is the variable that describes the motion. Actually, it gives us the position of something, a block, a mass, something, as a function of t. And I want to write my linear differential equations with this variable. And linear differential equation is a kind of differential equation in which x and its time derivatives appear only to their first powers. For example, this is a linear differential equation, but this isn't a linear differential equation because the x dot is a squared. So this is not a linear differential equation. And in this video, I want to solve some problems for you to see how the method works. This is our first example. X dot is equals to ax. So how can we solve this equation at all? First, we can integrate. Let me write it with another color, maybe green. Yes, green is good. Maybe we should integrate it. And if we integrate it, actually this equation is like this. So we put x here and dt here, and then we integrate. The natural log of x is equal to at plus a constant c, and x is equal to e to the power of at plus c, and it is equal to e to the power of c times e to the power of at. But the second method is a method that I'm gonna teach you in this video. It is guessing an exponential solution. You can guess the solution sometimes in solving differential equations, and here you can guess an exponential solution because one of the functions that its time derivative equals to a something times itself is actually this function plus a constant maybe. So we can use this and we plug in x equals a times e to the power of alpha t. So if we plug this in, we get this. The time derivative equals a e to the power of alpha t. These are cancelled and alpha is equal to a. So x is equal to a e to the power of at. And at 0, we have a, which is equal to e to the power of c, the constant that we described and defined in the previous part. So this was a simple linear differential equation, and we solved it using two methods. From now on, I don't use the integration method, and I want to solve more examples with this method. The method is really useful for solving hard linear differential equations. One of those differential equations that need some effort is this. This is really common. I tell you why. we have two situations. Let me write it with green again. We have two situations. First, a is greater than 0. In this situation, x double dot minus ax equals 0. And in this situation, we can put x is equal to a e to the power of alpha t, and we get a alpha squared e to the power of alpha t minus a e to the power of alpha t equals 0. So if we cancel these, we get alpha equals minus plus or minus the square root of a. And we can say x is equal to a e to the power of the square root of a t plus b e to the power of minus the square root of a t. Because if something is solution to linear differential equation and we have another solution too, then the sum of them is a more general solution to that differential equation, and the sum of them is actually a solution. So we have this for our general solution to this differential equation. And the second case is a less than 0. In this case, I define minus a equals omega squared. So x double dot plus omega squared x is equal to 0. This is actually the equation for a simple harmonic motion. But how can we solve this equation? And with this method, actually, I want to concentrate on this method. So how can we solve it with this method, with getting the solution? By actually doing this. Again, we put it in the equation, a alpha squared e to the power of alpha t plus omega squared a e to the power of alpha t equals 0. We cancel them. We get this. Alpha squared is minus omega squared. But what does it mean? It means that alpha is equals to plus or minus I, the square root of omega. And here, I is the square root of minus 1. This is imaginary unit. So, here, what should we do now? We have something imaginary in our equation, but we want to describe a real motion, actually real particles motion. So we shouldn't have imaginary terms, but what should we do now? So what we find is this: x of t is equals to a e to the power of I square root of omega. Actually, here I did something wrong. Here it is omega squared, and it is plus or minus I omega. So we have this general solution, but we have an identity which is this: e to the power of I theta equals cosine of theta plus I sine of theta. And you can prove this by checking the Taylor series of the left part and the right part. So we can use this identity here, and before using it, I should tell you something. When you plug 0 in this equation, you get a plus b, which is x at the 0, actually x at the beginning of the motion. So it is x naught. And if you take the time derivative and plug in 0, you get not minus, you get I omega a minus b, which is equal to v naught. So you can use these two equations to calculate a and b. I do that. From the first equation, you get a equals x naught minus b, and if you plug in into the second equation, I omega times a, which is actually x naught minus b, this equals v naught. So v naught over I omega is equals to x naught minus 2b, and b equals x naught over 2 minus v naught over 2I omega. And a is its complex conjugate, and a is like this. So we find a and b. Now I write my differential equation again with these terms. And here we can expand this e to the power of I omega t with that identity I gave you. and cosine of omega t time plus I sine of omega t plus x naught over 2 minus v naught over 2 I omega times cosine of omega t minus I sine of omega t. But here, if you actually see more carefully, we get x naught cosine of omega t plus v naught over omega sine of omega t, which is actually everything here is real. They are real numbers and they're describing a real physical phenomena, and the imaginary parts cancel. So this is the equation that describes simple harmonic motion. But this has some other forms too. For example, you can define another constant and use a cosine function with phi, or maybe an e times sine of something plus phi. And this is these are actually the other forms of this equation that you might see in textbooks. The third equation that I'm gonna talk about is this equation: x double dot plus 2 gamma x dot plus ax equals 0. And how can we solve it? Again, by plugging in a e to the power of alpha t as x. A alpha squared e to the power of alpha t plus 2 gamma a alpha e to the power of alpha t plus a e to the power of alpha t equals 0. So we cancel these terms and we get alpha 2 plus alpha squared actually plus 2 gamma alpha plus a equals 0. This is a quadratic equation, so we solve it. Minus 2 gamma plus or minus the square root of 4 gamma squared minus 4a over 2. I cancel 2 here. These are actually the roots. So we have again two solutions. So our x of t is like this: minus gamma plus gamma squared minus a times t plus b e to the power of minus gamma minus the square root of gamma squared minus a times t. And this linear differential equation is solved too. This video was a basic knowledge of linear differential equations. I hope you enjoyed the video, and don't forget to subscribe and like the video. Bye.